In this lecture, we will be covering modeling with differential equations. Modeling with differential equations exists pretty much everywhere in the real world. In predator-prey systems, mixing problems, Newton's law of cooling, engineering problems, money problems, vibrations, population growth, and many other areas, we use differential equations to solve real-life problems. And these differential equations are really easy to solve. When we have these problems, the only important part is to convert the words into mathematical differential equation expressions. Once we can convert the correct differential equation, it's just a matter of solving the differential equation, plugging the initial values and solve it. And just like every other example we did, the only thing is just modeling that differential equation. All right, so what we want to do when we're dealing with these problems is to understand the question and then interpret that question in a mathematical sense, put that in differential equation form, mathematical form, and then once we are in that form, we're just going to solve the differential equation, plug the initial values, and get ourselves the equation we are looking for. And in these problems, what we usually have is we are given a rate of change of something. This could be anything: a rate of change of population, a rate of change of an adding mixture, a rate of change of Newton's law of cooling, like the temperature. We can have different kinds of rate of changes, and we are usually given something is proportional to something else. And once we know the rate of change, obviously means the derivative, the slope of a function at a point. So we will have this rate of change function in a slope in a derivative form, and we will be setting that equal to, because it's in proportion to, a function we are given. It could be a function of x, function of y, could be both. It doesn't really matter. All we have to do is interpret that from the question and solve basically the differential equation, guys. And most of the time we can use integrating factor or separable method to solve these differential equations, because these are most of the time will be first order differential equations. In vibrations unit, we will sometimes have second order differential equations, but they're really easy to solve, and we have a bunch of methods to do that. But most of the time for this course, we are learning first order modeling with differential equations. So these are what we will be focusing on. Now here's a very nice problem, guys. Please pause the video and try to solve this problem on your own. This problem is telling us that a population grows at a rate proportional to its current size. This is an important information, so take a note. Initially, the population is 500. After 2 years, the population is 800. Find the formula for the population as a function of time. So we are asked to find P of t. Okay, this is the interpretation of the last sentence. Okay, find the formula for the population. It's asking us what is P of t. The third sentence tells us after 2 years the population is 800. This means that P of t equals to 800. Okay, we are given one condition and another condition. Initially the population is 500. What does initially mean? From the start, the population is 500. So at time equals 0, okay, at P of 0, our population will be 500. So this is the mathematical translation of this question, and the first sentence is telling us a population grows at a rate proportional to its current size. So we are given that dp dt, okay, the growth, the change, the rate of change of the population, or the growth, it doesn't matter. This just tells us that population is going in a positive rate of change. Okay, this means the slope is positive. Rate proportional to, when you see proportional to, this, like, we can interpret this as an equal to its current size. So it is proportional. We're going to have a constant here, a k, times its current size, which is a p, which is the function we're using. So This is really basic translation. If you can come to this point, this means you're actually capable of interpreting this problem, and the rest is just using math, differential equations, calculus to solve these problems. So now that we are given this problem, if I gave you all of these information, there would be a much easier question, because you would just go ahead and solve this differential equation, plug these initial values, and get P of t very easily. And this is what we're going to do right now. The only thing is you have to understand what the question is giving you. So guys, these questions can be sometimes challenging to understand, so just keep practicing, and I'm pretty sure you will master it in no time. So I want to start by solving this differential equation. So let's send this dt over to the right hand side and get our separable. We will use separable and divide this with kp. Kp equals to dt. Okay, now we can integrate both sides. Okay, I will pull that 1 over k out since it's a constant, so we will have 1 over k ln of p equals to t plus c, just like this. Now let's multiply both sides with k, so ln of p equals to kt plus kc. Okay, and taking the e power will give us p equal to ekt plus ekc. I'm sorry, this is a multiple. Okay, just like this. Now that we have this part, it is important to note that this e to the kc is actually another constant. It's because k is already a constant we will have in this differential equation. It's not a variable, since we could pull that out in the integral, so we will actually call this another constant c. And c multiplied with akt equals to p. This is the final form of our differential equation. And now this basically is what we're looking for. So we have our p function right now, ce to the kt. So I will just write that over here, p equals to ce to the kt. We just derived that. We took the integral by separating, and then we were able to derive this p function. Nice. Now we are going to plug our initial conditions to solve this differential equation. So we know that p of 2 equals to 800. Okay, so p of 2 equals to c e to the 2k equals to 800. Okay, this is one information. However, we're unable to find it because we have two unknowns in this equation, so that's why we are given another initial condition, p of 0. P of 0 equals to, if you plug 0 on the top, we will cancel this e to the kt factor, and we will just have 1, so it will be c, and this is equal to 500. So we can update our solution. P equals to 500 e to the kt, and p of 2 is now going to be really useful to us, so we will have 500 e to the 2k equals to 800. This gives us e to the 2k equals to 8 over 5, and ln of both sides, we will have 8 over 5 equals to 2k. Okay, I just took the logarithm of both sides, and dividing that by 2, we will have k equals to 1/2 ln of 8 over 5, just like this. And if you want, we can carry this 1 over 2 to the top, and k will be equal to ln of 8 over 5, and this will be to the 1/2 power. And now if we go ahead and plug that into our differential equation, remember, was 500 e to the kt, so 500 e to the ln of 8 over 5 to the 1/2 power times t. So this t can also go to the exponent since we're multiplying that. So instead of 1 over 2, I will have t over 2. And now that we are able to cancel this e and ln, this is a very smart move, guys, because I'm just getting these constants out from here to the exponent, so I can cancel this e and ln. Guys, don't try to cancel this when you have a t over 2 or any constant here, because you cannot do that. That's not mathematically true. These have to be, the constant of ln must be 1 so that you can cancel this. So now our differential equation will be 500 times 8 over 5 to the t over 2. And this will be, guys, equal to our p function. This is now showing us our population growth. Well, important thing to notice, we know that population was growing, and this is a growing example because look at this. We have a exponent here, and our inside is greater than 1, so apparently as t approaches to infinity, this expression also approaches to infinity. So this is actually a growing function. And we can, if you're not sure of if you're doing it right or wrong, what you can do is p of 0 equals 500, right? So just plug 0 to t. If we have 0 on the exponent, obviously that's 1, so our p will be 500. So it does satisfy this initial condition. Now what is our second initial condition? P of 2 equals to 800. Okay, P of 2 equals to 800. Is P of 2 equal to 800? Well, yeah, because P of 2 will be what? 500 multiplied with 8 over 5. Okay, 2 over 2 is 1, so 8 over 5 to the first power, which is 8 over 5. And 500 times 8 over 5 is obviously 800. So it does satisfy this equation as well. This shows that we did not make a mistake, and this is the correct population growth expression in mathematical terms.